Hi, in this video I'm going to show how to generate C and C++ code for reinforcement learning agents trained in MATLAB and Simulink. As you might know, reinforcement learning is very useful for control systems, which usually are deployed in embedded systems. This can happen in robotics, vehicle controls, house controls, etc. Or like this motor controller that you see here. These hardware embedded systems usually have compilers for which you can take C or C++ code and compile it into an object file that is deployed in this hardware. That's why code generation is important for this. Reinforcement learning agents, when trained in MATLAB and Simulink, we cannot generate code from them as they are. We have to generate a policy. Okay, what's the difference between policy and agent? The agent, when trained, is going to take as an input a reward, a termination signal for the episode, and the observation, and the output is an action. The policy also takes an observation, but that's the only input. Only observation and the action. You don't need the reward, you don't need the termination signal, because those are only used for training. The policy is the agent already trained. So that policy can generate, we can generate code from that policy. And the MATLAB Reinforcement Learning Toolbox offers two alternatives to generate the policy. One is the generatePolicyFunction, which generates a function to call the policy, and that works for MATLAB code generation and Simulink code generation. The other alternative is generatePolicyBlock, which generates a Simulink block, which naturally only works for Simulink coder. So let's show this. I'm going to show these alternatives now. First, I'm going to generate the policy function for this agent to control a vertical bar using a cart. I'm gonna put as a reference in the description of this video a link to another video showing how to train this reinforcement learning agent in particular. But that's not gonna be the focus on this video. I'm gonna assume that the agent is already trained. So I'm gonna load the agent, and this is basically, well, I'm gonna use another command instead of this. You can see in this folder of this example that we have this file. This is the agent. So I'm gonna load that file. You can double click it or just execute the command indicating that you want to load the agent, this particular variable, which is for the agent. And that gets me the agent in the base workspace, and I'm gonna create a policy for it and use MATLAB coder to get the C++ code for it. Before generating code, I have to create the policy, and for that I use the generatePolicyFunction, which is the function that I just mentioned. The only argument is the agent, which is in the base workspace. And when I execute that, there's going to be a couple of files. One of them is the data that carries the policy for that agent, and I'm going to put cancel here to avoid issues. And the other ones is the policy function for which I'm going to generate code. Notice that the input is the observation and the output is the action. And there's going to be, in the script, there's going to be a global variable that is a persistent variable, and that is that's going to use the coder.loadRL from reinforcement learning, loadRL policy, which is going to load the policy from the math file. So I'm going to show how it works. So I'm going to load it from the created math file that was created with this function, and I get a reinforcement learning policy object. From that policy, I can call this method, get action on it. This is actually a method, so I'm going to use it in the method form. But first, I'm going to create an input. Before that, I'm going to find out the size of the agent for this problem. Let me show agent. You can see the observation info in here. That's what I want, observation info, and you can see that it's 4x1. If you remember this example, the observations are as you can see in here, the position, the velocity of the position, the angle, and the rate of change of the angle. So I'm going to create a vector of 4 variables of ones, and I'm going to multiply by 3, and then I'm going to feed those to the policy. So you're going to see that this is a method on the policy object, and I pass the input that I just created, and you can see the action that is going to be a 10. That's the force. Remember that in this example you have two possible actions, a positive 10 Newton, negative 10 Newton, indicating that you're taking the card to the left or to the right. So you can see that it executed the action. So basically that's about it. It's going to use this, load this a policy only once. That's why it's a persistent global. So if it is empty, it means that you have not initialized it, and then you're gonna initialize it, and then that's gonna happen only once, and for further calls it's gonna get the action from the observation, and this is what you're gonna get in the code generation. So now let's generate code for this function. MATLAB Coder, to generate code using MATLAB Coder, you have to use the codegen command, and the codegen command requires a configuration, and I'm gonna use the MEX configuration. It has a bunch of parameters, as you can see. One of them is the target language, and maybe you can see it around here. You can see the target language is C, and I could change that target language to use C or C++. I'm gonna keep it in C. And for the configuration, the deep learning configuration, I'm gonna use a Coder deep learning config none. I don't want any deep learning library, because this agent is using a deep learning network, deep neural network, for the policy. You can see in the example of the description, if you go there, you're gonna see that it uses a bunch of fully connected layers connected together to predict from the observation the action. So I want to use the default code generation for this particular case. I'm gonna use a library later. I'm gonna show you. And now I need an input, and the input is going to be once, basically the same thing that I just did moments ago. And the reason why I need an input for the function, it's not because the code generation is going to call it, it's because it's going to infer the types from the input. In this case, it's going to be a vector of real values 4x1. So that's the purpose of it. You can alternatively specify the types directly, but it's kind of easier to just provide a sample input value so that the MATLAB coder can infer the inputs. Because if you notice in here, this can be any type. This can be an array, this can be a matrix, this can be a scalar, it could be integer, it could be real, it could be anything basically. And MATLAB coder just doesn't know what to do with this. So if you specify an input, then it says, okay, you're gonna expect, because you cannot do that, actually you cannot do that efficiently in C++, basically have any type. You have to have a type in C++ to make it efficient. So that's why we need to specify an input. So I'm telling it, okay, you're gonna have an array of double 4x1, and that's the case always. So we don't have to make it inefficiently dynamic. Okay, so the codegen command is gonna take the configuration that we just created, take the name of the function, which is this one, evaluate policy, the input that I just created, yeah, it could be this one or the one that I just created before, and then indicate that I want a report. So let's see the code generation. Let's execute it to take a look. You can see that it takes a while, and all the artifacts of code generation are gonna be under this codegen folder. Let's just cancel this to avoid issues. Okay, finish, and we can access the generated coding here, and the entry point, you're gonna find it through the name of the function, evaluate policy. So you look for a file name evaluatepolicies.c, because the target language is C, so we're gonna have a C file, and in here you're gonna have the computation for the neural network is not any library, so basically it's computed like this. You have an action set, and it computes an index, and from that table it's gonna take the action for that particular observation. The observation is gonna be the input. Yeah, somewhere here you can see observation is the input, and the output is the action. There's gonna be an initialization method where the neural network might be initialized, but maybe not in this case. So now let's do a little bit different. Let's, instead of using no library, let's use Intel MKL. This is a library for deep learning, but this library requires the target language to be C++. So let's say that is C++, and let's use exactly the same command. I just changed the configuration, but just to be safe, I'm gonna just delete the codegen folder. Cancel here. Okay, now let's codegen. Okay, finish, and you can see the artifacts again in here. And if you want to deploy this into a embedded system, then this is the place where you find your artifacts to deploy. Deploying to particular hardware, depending, you have to do additional work depending on the particular hardware. MATLAB usually have hardware support packages. For example, if you want to deploy this to the Android device, to an Android phone, then you can use the Android support package to generate code for that particular device, or Raspberry Pi or Arduino. There are different support packages to be able to deploy the generate code into those devices, and sometimes automatically, like in Android, it automatically deploys it to your cell phone. So, but the workflow is similar. You're gonna generate a C++ code or C code in a similar way as what is happening right now. Okay, so you can see that I chose to generate a report like last time, but I didn't open the report. Let's open it this time to see the artifacts. And you're gonna see a similar view to the one that you see in the folder browser. And you can look for evaluation policy. This time it's a C++ file, so you're gonna expect a CPP file, which is this one. It's gonna ask you permission, and you can see that this time in the entry point function, which is with the same name of the evaluation policy, you get the observation as input. You instead are gonna get a call to the predict DL network predict. This is because of the Intel MKL library that implements the computations of the neural networks in their own way, and you can see it in here how they call the activation for a particular neural network object given as an input. Here it's gonna call the activations of each layer, and at the end it's gonna copy the output with this memcopy. So that's basically using the Intel MKL. So now let's generate GPU code for this. So I'm gonna again delete the folder. And for the GPU, you require a different configuration. So let's create that configuration. Okay, I'm gonna look for it. And notice that to generate a regular C++ code for CPUs, we use coder.config. This is the normal MATLAB coder workflow. But for GPU, it's like this. Is coder.gpuconfig, and I'm gonna generate a MEX. The importance of the MEX, I didn't mention it earlier, is because you're gonna generate a MATLAB executable, and that's what's gonna happen is that the C code that you generate is compiled, and then MATLAB generates an interface around it so that you can run your executable within MATLAB. That's the advantage. This is not deployment per se, but it allows you to test your generate code before you do the deployment, as I mentioned before. Okay, so let's create a library for it using the CUDA DNN. This is for deep learning. That is because we're gonna generate a CUDA code, and the target language is C++ again, and the command is exactly the same. So let's run it. For generating GPU code, it takes a little bit longer to run that for regular CPU code generation. Okay, finished. So let's take a look at the report. And instead of having a CPP or C file, we're gonna see a CU file, evaluate policy. And you can see also you have an entry point with the same name given the observation. And you can see that it's gonna call again DL network predict. The cuDNN library is gonna implement the neural network computations, and you can see the kernel, the syntax of CUDA in here. You're gonna see the GPU CUDA malloc and things like that. Okay, so that's for GPU code generation. And now since I have a GPU, I guess I can test it, so I can try running it. The final MEX file is here, so I should be able to do this. Given the observation, giving me the action, I should have been able to do this for all of the other alternatives. That's the purpose of the MEX, so that I can call the compile executable from MATLAB. And you can see that it gives the same answer, so the generate code is correct. Okay, now let's do code generation from Simulink. for generating the policy block, I'm going to use this example, and all of this example I'm going to share in the description as links in the description of this video. Okay, so let's just open this example. I'm going to discard my previous changes. I'm just going to go to the desktop, and that'll take me here. Okay, so I'm going to open the model that has the reinforcement learning agent, and this model depends on all these variables which are particular for this example, in which we have a motor, in which the motor controls an inverted pendulum. So all of these parameters are required. Just gonna run them to load them, and I'm gonna load the train agent. The agent is already trained again, and then I'm finally gonna open the model. You can see the modeling here, and usually in Simulink or a MATLAB environment, you just want to generate code for the controller, not for the whole simulation environment, because in the end the controller is gonna interact with the physical world. So these things are modeling the physical world, and we don't have to generate code for them. We're interested only in this part. Okay, so let's go to the controller and the control system, and inside of it you're gonna find the reinforcement learning agent in here, and you can see that the agent is gonna take, as I mentioned before, it's gonna take the observations, but also the rewards and the termination signal, and this is only needed for training, not for code generation. We cannot generate code for this controller. So when you double click on the reinforcement learning agent, there's going to be an option to generate a greedy policy block. So there's not going to be exploration in this, because the exploration is good for training, but if you're not training it, then it can go greedy on the policy. So let's just click it, and when we click it, we're going to get a block created, and we can replace, we can delete these signals and delete this block and just put this block in here, and it just will work. I'm gonna show you that already done in a separate model, but that will be the workflow. And you can see here, you double click, you're gonna see the math file for the policy, like in the previous example in which we have a MATLAB function loading a policy from a math file. This policy block also loads the policy from a math file, and this is the name of the file. So when I double click on here, on this place, we not only create the block, but also create the file. So if you go back to the to here, you're gonna see the math file. So I'm gonna do it programmatically instead of doing it with the reinforcement learning block GUI. One of the advantages of doing programmatically is that you can set the name of the math file for the policy, and you can see for the agent in here, when we clicked on generate greedy policy, it means that there's no exploration. It did what I'm gonna do automatically. Notice that I'm doing agent.use exploration policy set to false. Okay, when I'm doing programmatically, I also want to generate it greedy by doing that. Okay, the file name is gonna be this one, and I don't need to execute this because the file doesn't exist. So I call the generatePolicyBlock. This is like the other function called generatePolicyFunction, in which I pass the agent, the train agent, and you can optionally say the name of the file. We probably could have done that for generatePolicyFunction as well. And you can see there's a now I get the math file for the policy, and I get the policy block, and if I double click, you can see that particular file is what this particular math file for the policy is what the policy block is pointing to. Okay, so I'm gonna close that because there's another model that is already using this, and it's this model over here, and I'm gonna show it to you. And you can see it's the same control, it's the same thing, same control system, closed loop, same thing, reinforcement learning subsystem. And you can see here that it's more simpler, only has the observation and the output is the action. So the reward and the termination signal went away. So this controller is going to be called from another model, and it's going to be called as a reference model, so that we can generate code only for this reference model and not for the whole model that is doing the simulation of the environment. So let's open the model that has is this model over here. So this model is referring to the other model. So this is a common workflow, as I mentioned before. So you can see the controller in here, and we just want to generate code for it, for this. If we want to generate code for everything, then I can do rtwbuild for everything. Actually, I can do rtwbuild for this particular controller separately. For example, if I open like this, I do here bd root, and you can see that this is my control system. I can just hit F9 and that'll take me to the controller. So I'm gonna generate code for it, rtwbuild bd root, and you're gonna see the generate code for it. Okay, it took a while, but you can see that code generation went without any issues. And you can see in the name of the model, in this case, since this is GRT, you're gonna get underscore GRT and RTW at the end. If you were ERT, then you get ERT here, and then you can expand this, and you can look for the name of the model here, .c, and you can see that is this one. This is the entry point, the one that has the name of the model, similar to MATLAB core, where is the name of the function, and there's gonna be a step function around here, or the name of the model. So this one, you can see the predict. Actually, this is to call the neural network. So depending on the configuration, it can use the Intel MKL library, or it can use the default code generation for the particular network. So in this case, you can see the computations here of the network. We are using the default generated code because when you go to the config set, if you hit modeling, config set, and that'll take you to here and go to code generation interface, you're gonna see that target library is set to nothing. If this is set to Intel NKL, then you're gonna get the Intel library, which is more efficient most of the times. But for this code generation, I use the default implementation, the default code generation. But the entry point is the step function, and you can find it down here. You can just search for step, I guess. You can search step. There you go. This is the entry point, and eventually this is gonna call predict somewhere. Yeah. This is the output. The output is coming from here, from the global variable. So yeah, this is actually is a subsystem. That's why this subsystem is the one that eventually calls the predict. If you go to here, you can see that the predict is down here. Yeah, so yeah, you can see it in here. The predict is called from this subsystem. Okay, yeah, that's about it. But generate code is not enough. I mean, well, it's good if you want to deploy. Again, there are support packages for this. Even for Android, you can generate code from Simulink and automatically deploy it into your cell phone. And for other targets, you can do the same as well. But before doing the deployment, you want to verify that your generate code is correct, and that for that, Simulink offers software in the loop. Software in the loop is going to do something similar to MEX in MATLAB Coder. In MEX, you could execute the compiled generated code within MATLAB to verify that it is numerically equivalent to a MATLAB function from which you are generating code. In software in the loop is something similar. The generated code is going to be compiled and called within the Simulink environment, and so that you can compare the numerical output against the normal simulation of the Simulink model, and that way verify that the generated code is giving the right answers. Okay, so let's do a software in the loop in here. I could do it software in the loop for the whole model in here by just going to apps, going to seal build manager, and then use on the top models and just verify against normal simulation and run verification. But the problem is that I have 0 inputs, and 0 input is equal to 0 output. That doesn't offer any value. So it's better to run it within the whole simulation environment that we have for this. And that's the importance of the other model that I showed, which is this one. And this one is calling the reference model. This is calling the reference model that we just generate code for. But this is going to call it from here. But again, we don't want you to generate code for everything. because this control system eventually is going to interact with the physical world, so we don't need all the simulation around it. We just need the control system. How do we do that? We cannot generate this. We cannot generate seal for the whole model, generate code for the whole model. We want to do it for that particular block. If you do right click on the model reference, you go to the block parameters, you set the simulation mode to seal. And now you're gonna see the mark of seal in the block. What that means is that we're gonna generate code only for that block, and the rest is gonna go in normal simulation. And we're gonna compare the results of that block in seal and that block in normal simulation. Again, we go to the seal manager the same way that we did before, to the apps, and instead of putting top model, I'm gonna put model blocks in seal build mode. So only this is gonna be in seal. The rest is gonna be normal simulation. So and this is going to be compared against normal simulation. So let's run software in the loop verification now and take a look at the results. It's going to take a while because I'm generating code for the control system. After seal finish generating code and running the simulation, we're gonna get this window pop up with the result for comparison. And you can see the blue one. If we click on the blue one, we get the result. So this is the speed of the system that we want to control. And if we click on this is the blue one is normal simulation, and the red one is software in the loop simulation. And you can see that they are almost identical. And it is impossible to get exact numerical match, especially when you're doing computations on real values because of the rounding. The generated C++ code rounding is going to be different from the one that Simulink does. So it's expected some noise, some small error. So for that we have a tolerance. So the error has to be smaller. The difference has to be smaller than the tolerance, which is 8 multiplied by 10 to the negative 5. So it's very small. And you can see that the difference between the two signals is below always that tolerance. So they are practically the same. And you can notice that both signals are almost the same because the error is so small. Okay, so that shows how you can make sure that you generate code for your controller within Simulink is numerically correct. So I show you how to do a policy block for reinforcement learning agent, but now I'm going to show you how to use a policy function within Simulink, and you do that by using a MATLAB function block. I'm going to show that in a moment. For that, I'm going to use this example. I'm just going to open it. I'm going to open these, the parameters that are needed, and just open the model for this. And this take me to here. You can see again a similar pattern. We have a simulation environment with sim mechanics for which we don't want to generate code. We just want to generate code for this reference model. And if you go inside, you're gonna see that we have a couple of agents. You have to. We're gonna use it's gonna use variants in various places. It has a reinforcement learning variant and a deep learning variant. Okay, so if you go inside the mask, by hitting Ctrl U, you're gonna have the couple of agents. One of them is to select the mode, and the other one is to control the pendulum. For both of them, you're gonna have a variant for deep learning using the predict block that is using a neural network. I'm not gonna focus on that because the focus of this video is in reinforcement learning, which is this one. And you can see if you go to this block, you're gonna see the MATLAB function block. Within the MATLAB function block, you're gonna have a simple function that takes as an input the observation, just pass it to this function, and take as an output the action. So that's how you integrate it. It's very simple. Basically, you're gonna call the same function that we use at the beginning of this video, generatePolicyFunction. You pass the agent, which is the agent in the base workspace. You indicate the file where the policy math file is gonna be, the name of the function, and you're gonna, in this case, there's a couple of agents, so you just call it for each agent. And once you have it, then you go to create a MATLAB function block, and then just call it from there. That's about it. And then you use seal in the same way. It could be as a seal block. It could be rtwbuild for generate code for the whole model for the case of the controller, or using CLOD at the top level. You can use various alternatives to deploy your generic code, but having the function in the MATLAB function block like this is an alternative. The other alternative is having a policy block. Okay, so that's it for the video. Thank you.